Welcome to not our second lecture on optimization problems, but segment 2 of our first lecture. The last segment ended with an explanation of why an obviously correct solution to the 0-1 knapsack problem was computationally intractable. I didn't prove it, and I'm not going to prove it, but the problem is inherently exponential. That means that there does not exist a solution that's guaranteed to run in better than exponential time. So what are we to do? Well, we could give up, but that's not really in our nature. We could try an approximate solution, and we will look at that, or we could look at an exact solution that's not always fast, but is often fast. We'll look at that in this lecture too. So now let's look at an approximate solutions. And in particular, I want to look at a class of approximate solution known as a greedy algorithm. Here it is. It's very simple. While the knapsack is not full, we put the best available item into the knapsack. When it's full, we stop. We have some contents, not guaranteed to be optimal, but often pretty good. We still have a question, though. What does it mean to put the best item in? What does best mean? Is it the most valuable? Is it the least expensive? Or maybe it's the ratio of the value to the expense in some units to be determined. Before we look at the algorithm, let's look at an example. You're about to sit down to a meal. You know how much you value different foods. For example, maybe you like donuts a lot more than apples. I know I do. But you have a calorie budget. For example, you don't want the meal to consist of more than 800 calories. Deciding what to eat is just a knapsack problem. You want to maximize the value to your taste buds, subject to the constraint of, in this case, 800 calories. So let's look at a sample menu. I've got some food here with pretty arbitrary values. The calories are actually pretty accurate. Now let's look at building a program that we can use to decide what food we should order from this menu. Now, as we look at the program, I hope you won't be surprised if I start out not with an implementation of a greedy algorithm, but with a data abstraction and then a helper function. After all, remember that learning to be a good programmer is a big part of this course, and modularity is a very important aspect of good programs. All right, let's start with class food here. Almost nothing of interest here. It's a very simple init function. Takes the ubiquitous self, the name of the food, the value of the food and its weight, and stores it in these attributes. We've got the usual getters of get value and get cost. And we can get the density, which we just talked about, by dividing the value by the cost. And finally, there's an operation that we'll be using to print the values of food. Now that we know how to make food, we need to make a menu. Again, it's very simple. It takes in 3 lists: the names of the food, the values of the food, the calories. These lists are all the same length. And it then just iterates through the 3 lists, creating food and putting it into the menu, and then returns the menu. All right, now that we have these 2 abstractions, let's look at some code that does indeed find a set of foods. So here's our implementation of a flexible greedy algorithm. What makes it flexible? This parameter called key function. This makes our implementation independent of the definition of best. All that's required is that key function defines an ordering on the elements and items. We can then use this ordering to decide what we mean by best. We do that here when we sort the items. Notice that we use sorted rather than sort. You might recall that sorted is a function that returns a list, whereas sort sorts the list in place. We use the function because we don't want to modify the parameter. We don't want to change the menu. We want to get a copy. And the copy is different in that rather than in some arbitrary order, the elements are in order going from best to worst. Why is it best to worst? Because we're reversing it using this parameter. And we're using the key function to decide which elements are bigger or smaller than which other elements. Once we've done this, all we have to do here is iterate over the list. Because we're iterating it over in order from best to worst, all we have to do is keep checking. If we have room to put the next item in the list into the knapsack, we do it. And then we go on and continue until we run out of room. Once we have the food in the correct order in items copy, we then iterate through the list from, in this case, best to worst. The only other interesting part of the code is this piece here, where we decide whether we still have room to put it in. If we do, we put it in. If not, we go get the next one. And since we're always looking at the best available, when we're done, we know we've made the best possible choices given our greedy ordering. Recall that we resorted to using a greedy algorithm in the first place, which might or might not yield a truly optimal result, because we were concerned about efficiency. So now let's see if this algorithm actually addresses the problem of exponential complexity. All right, here's the same algorithm but without the comments, so things are a little easier to see. Let's look at it. First thing we see here is we're calling sorted. That will certainly use some time. How much time will it use? Well, we know that sorting can be done in n log n time, and in fact is done in roughly n log n time in Python, where n is the length of the list of items. So we now have a lower bound in the complexity. It can't possibly be better than that. Could it be worse? Well, maybe. The other place we have to look at is here, where we iterate over it. That's the only other place we do anything more than once. But that's only order n, and we know that n log n plus n is order n log n, which mercifully is much less than 2 to the n. So indeed, we do have an efficient algorithm here. All right, let's use this efficient algorithm. We'll use it calling test greedy. Nothing very interesting here. It takes 3 arguments, the items, the constraint, and the key function, what we mean by best, and calls greedy, and then prints the result. Slightly more interesting is this function test greedies, which calls greedy over and over again. So the first thing we're going to look at is greedy by value, and we notice that it calls test greedy with foods, matched units, and the method food.getValue. Then we look at this one, which is going to go greedy by cost. This is slightly more interesting. And it's interesting because of the use of lambda. Let's look at what lambda does, and then we'll come back to why we needed to use lambda here. Lambda is used to create anonymous functions. That is, functions that don't have names. So think of it as it's an expression. The value of the expression is a function. The way we write it is we write the word lambda, followed by a list of arguments, and then an expression using those arguments. And it returns a function of n arguments. And what that function does is evaluate the expression on whatever arguments it's passed. That's a little bit fast. Let's look at some examples which should make it easier to understand what's going on here. So let's first start with the really simplest possible lambda expression. I'll assign f1 to be lambda x colon x, simply the identity function. Whatever you pass in, that's what it returns. I can now call f1 with 3, gives me 3. I can call f1 with a string, because certainly the identity function is polymorphic. It works fine. All right, let's look at a slightly more complex lambda expression. I'll assign this one to f2. This will have two arguments, x and y, and it will return their sum. Again, nothing very fancy here. So now if I call f2 of x comma y of 2 comma 3, it'll give me 5. And I can do this as well. Because you'll recall that plus is polymorphic. It does addition in numbers and concatenation on strings. So that makes the new function I've created using lambda also polymorphic. So I now get Annabelle here. All right, finally, let's look at a bit more complicated one. We'll call this one f3. Lambda x comma y, and here it's going to return the string factor if the expression x mod y equals 0, that is to say if y is a factor of x. Otherwise, it will return the string not factor. So this is a construct you may not have seen before. We've seen if-then-else commands in Python, but you can also write if-then-else expressions with this slightly strange syntax that I've shown you here. So we've now done that. So now we can look at the value of f3 of, say, 4 and 2. Sure enough, 2 is a factor of 4. Or we could look at f3 of 4 and 3 and discover that 3 is not a factor of 4. All right, that's lambda expressions. They're wonderful, they're useful. You can write amazingly complicated lambda expressions, and some people think they're beautiful. The truth is, you shouldn't. If the lambda expression is more than just a line, it's too big. Go back, use def, and write a function and do it that way. It's really much better. Okay, going back to greedy, we could ask the question, why did I use the lambda expression here in the first place? Why couldn't I just use getCost as the key function? Because it would cause the list of items to be sorted from most expensive to least expensive, which for most of us is actually the inverse of best to worst. I suppose there are some affluent people who think the more expensive the better, but most people are not in that camp. Hence, we use lambda to actually do the inverse of getCost in line here. Okay, let's run it. So what's going on here? The first few lines just have the names, the values, and the calories. I then use those to get a menu of foods. And finally, we call test greedies with a budget of 750 calories to see what we get. All right, the moment of truth. We'll run it. All right. Notice what we get is 3 answers. For greedy by value, finds a burger, pizza, and wine for a total value of 284 units. Greedy by cost does better. It finds a more complicated menu, apple, wine, cola, beer, and that ever popular donut for 318. And as it happens, greedy by density finds the same solution. Well, why do we get different answers? Well, because what we're doing here, and what all greedy algorithms do, is they make a set of locally optimal choices. That doesn't always give you a globally optimal solution. So we can see this with a little hill climbing exercise. So we might think that the way you get to the top of the hill is by just always going up. If you get a chance to go up or down or sideways, you go up. And maybe you go up the steepest possible path. Well, that works fine if we start, say, here, and we'll find our way to the top. But if we start here, we'll find our way up to here. And from this point, everything is downhill. So we're just stop. So we're here in what's called a local optimum. And we don't get any better. And that's what a greedy algorithm does. It might find an optimum, but it won't be the best necessarily. Well, in the example we just looked at, greedy by cost and greedy by density gave better results in the sense of more value for the same number of calories as greedy by value did. Is it always the case that one is better than the other? No. You might think greedy by density should always be a winner, but it isn't. And to show you that, let's try another example. Let's change this 750 to 1,000. See what we get. So here you'll see that, in fact, greedy by value was the winner. It gave us more value than the other two for that number. So there's just no way to tell. You get an answer. You don't know whether it's optimal. So should we use greedy algorithms? Is, as Michael Douglas once said, greed good? It's easy to implement. It's computationally efficient. But it doesn't always yield the best solution. We don't even know how good the approximation is. How close is it to the best solution? So in the next lecture, we'll look at what do we do when we really need to have the right answer and find out how to get truly optimal solutions.